Hi everybody. We're going to take a look at limits, just a quick introduction to the extent that standard level has to understand them, their notation, what they are telling us to do, what they're telling us to find, and really just looking at this graphically. Higher level, you're going to have to be able to do this algebraically and look at a few different situations with that. But for now, we're going to use our calculators and technology to see what this looks like as we graph the functions. Here's an example of a function we've maybe seen before. When I graph this, it looks just like a line actually. You see up here in the top, here's a line. But if we were to zoom in, what you would be able to see down here is that we actually have a hole at x equals 1. So if I were to trace along this function as I get infinitely close to it, here I have a few different values, I can tell what it's going to try to do. But obviously, because I can't put 1 into that function, because it will give me 0 in the denominator, I'm not going to be able to just find the value there. However, what I can find is the limit. If we do get really close to this, and it's not just essentially this line of x plus 1 where x doesn't equal 1, then we can find the limit, even if the value is not defined at x equals 1. This is the formal definition and notation of limits. You see that we have x getting very, very close to a certain value. If we have after the number as a superscript this negative, it means we're approaching it from the negative side to the left. And if we have it with a plus at the top in the superscript, it means we're coming at it from the right. And if there's nothing in the superscript to the right of it, then it means we want to find the actual value of the limit. Okay? And that only exists if the value is approaching it from the left is equal to the value approaching it from the right. Here you see an example. This is called a piecewise function because it's made up of different pieces. It doesn't all have to have different colors, but I've put them in different colors here so you can see the different pieces. And here are a few examples. This one here is going to say, well, what is the value of the limit as x gets really close to negative 2 from the left? What's the value of the limit of this function? This whole thing is the same function made up in pieces as I approach negative 2 from the right. And can I find then the limit as x approaches negative 2 in general of this function? And then the same thing for positive 2. It's really easy to get confused where this negative is in front of the value that we're approaching. That would then mean it's the negative 2 and not positive 2. Whereas if it's the superscript after, then that means we're approaching it from the left or from the right or the general value of the limit. So you see the value of this limit as x approaches negative 2 from the left will be as if I sneak up on negative 2 coming from the left, I'm going to approach the value of 2. There it is. And if I approach it from the right along the red function here, I'm getting close to negative 2 from the right, it also is going to equal 2. And since both of those are equal, the limit as x approaches negative 2 of this function is equal to 2. If I instead look at the value of positive 2 for x and I approach it from the left, it's also going to approach 2. That's a coincidence, basically, just because of the parabola. That's not that that's always symmetrical or equal. However, if I approach the value of 2 from the right, which is then along this green function, I'm going towards 4. That means that the limit as x approaches 2 over all of the function doesn't exist. We can write that as DNE, does not exist. We're going to take a look at a few different examples here. These ones on the left are just different examples of what we might find as problems or no problems in finding limits. Again, just using a graph for today. On the right, we have the same function, a piecewise function. This is the notation of a piecewise function made up of different pieces, depending on what domain we're looking at. We're going to look at them with graphs. Excuse me. So here's the first one. Can we find the limit as x gets close to 2, so overall from the left and from the right have to match, of this function x cubed minus 5? And we can, because it's defined. When you don't have any issues and you don't have any asymptotes or holes, any discontinuities, finding the limit is really just the value. So as I approach x equals 2 from the left, I get close to the value of 3. As I approach it from the right, I get close to the value of 3. So the limit equals 3 here. It's the same as just the value of the function. The next one, though, we may notice that we have a problem, because as x goes to 3 in this function, I'm going to be getting 0 in the denominator. The function looks like a line, but actually the value at 3, as I said, is undefined, because the denominator would be equal to 0. However, if you were to just take a look at what's happening on the left and the right, it will be fine to ignore the whole essentially and say, well, as I get close to 3 from the left, I'm getting really close to the value of 7. And as I approach it from the right, I'm getting really close to the value of 7. So we can say that the limit equals 7 even if the function doesn't there. If you were to find this algebraically, we would be able to simplify it. Higher level, you'll see this in the next one, where we could factor the numerator into x minus 3 times x plus 4 and cancel the x minus 3's and just get x plus 4 and put in the value and see that we'd get 7. But the original function did have that problem. This last example here is going to do something even weirder. It has an asymptote. So what's happening as x approaches 0? Well, it has an asymptote, which we can write as a line. But as I approach x from the left, from the negative side, I'm going to positive infinity. And you can have a limit that goes to positive infinity or negative infinity, but they have to be equal on both sides. And the limit, as I approach 0 from the right, is going to negative infinity. So in this case, the limit doesn't exist. Now let's take a look, similar to the first example, at this piecewise function. It's made up of a piece where if I'm at x less than -1, I'm going to have this normal parabola. And if x is greater than or equal to -1, then I will have this line. Here's what it looks like if I'm graphing it. A lot of times these do touch, they're continuous. In this particular case, they're not. And what could that mean for the limit at this case? You probably already know. The limit as x goes to -1 from the left is going to be fine. It's going to be equal to 1. And the limit as I approach -1 from the right is also okay. We're going towards 4. But because those two things aren't equal, we're not approaching any whole. Okay? So it doesn't exist, the limit. We've looked at rational and reciprocal functions where we have asymptotes, vertical and horizontal. Higher level, you've seen oblique asymptotes, and we can think of these as limits as well. Okay, vertical asymptotes, the definition of a vertical asymptote with regards to limits, is if the graph of a function is either approaching the limit as positive or negative infinity as x gets really close to some value on the left or right, or as it goes to positive or negative infinity, I guess that's the same as left and right, I just kind of combined it in my thinking, then we have an asymptote as things are going to infinity vertically. Okay, I'll go back in a second and show you what I mean by that a little bit more clearly. And a horizontal asymptote is switching where we see the infinity and where we see the real value. Okay, so what this is saying is x gets really close to -3 from the left of this function. Okay, then we'll see that, I don't think I can go back on here. No, I can't go back. As we're approaching -3 from the left, remembering the function, I think I'll just give you here. As we approach -3 from the left, here it is, I'm going to sneak up on it, we are approaching positive infinity. And if I approach -3 from the right, we're approaching negative infinity. That's how we have a vertical asymptote. If we're looking at the horizontal asymptotes, what's happening as x approaches negative infinity? Well, as x approaches negative infinity, I'm going over here, we're approaching 4. Remember that we can see these by comparing the coefficients of the highest power of x, so 4 over 1 in this case. So it's approaching 4. You could trace on your calculator if you'd like to. And we can also see as we approach positive infinity that we are getting very close to 4 as well. What's important is to not confuse that this means the limit going to infinity, kind of as x approaches infinity, is 4, because it doesn't mean we're approaching it from the left side or from the right side. You can't approach negative infinity from the left and from the right, okay? So it just is in this particular case. They are both approaching 4 though, and that's the definition of this asymptote. It doesn't have to be that you're approaching it, approaching k from both, let me go back. It doesn't have to be that you're approaching k as you go to negative infinity and positive infinity. As you think of an exponential function, for example, you'll only have this horizontal asymptote as you approach perhaps positive infinity, whereas negative infinity you may actually not even have in your domain. We also could think of limits as something else we've done. We've looked at geometric series that approach a convergent value. If you have a defined limit in a real number, being a real number as n goes to positive infinity, so as you add an infinite number of terms in a geometric sequence, then we talked about this converging. That would mean that the limit exists and it's a real number. It's not going to just infinity. If we have it approaching positive infinity or negative infinity, then we said it diverged. We can combine these ideas together. This is really kind of getting in towards a higher level idea, but you can still see it. We can calculate the limit as n goes to infinity. This is a geometric series calculation here. What is the sum of these of an infinite number of terms? We could say that this is the sum of an infinite number of terms, and we know based on the structure of this that u1 would be 2 and r would be 2/3. So we could find it because r, or the absolute value of r, is less than 1. That was, if you remember back to geometric series sequences, for infinite series, that was the key feature of being able to calculate this. And just finding the math of this, that would then equal 6.